Good morning, calculus class. This is Miss G. It is Thursday, April 30th, the end of the month. Okay, well, today we're starting a new section, section 5.6. I didn't have any requests for homework problems, so I'm hoping that you did well with those yesterday. Today's topic, the general description is the definite integral as the limit of a sum, but actually what we're focusing on is something called the midpoint rule. And let's talk about that. And by the way, you can use calculators on this whole assignment. Let's suppose you want to evaluate a definite integral, which you've been doing, but you can't find an antiderivative of the integral. Then you can use an approximation strategy because you've been adding 1 to the exponent, dividing the coefficient by the new exponent. You've been doing reverse power rule, but sometimes you can't do that. The functions are different kinds of functions. And you can't find a function that when you take the derivative of it, you get your integrand. So this is an approximation of how to find that area. It won't give you the exact area like the integral does, but it will give you an approximation. And how do we do that? We divide our bounded region into rectangles and find the area of each rectangle and add up all those areas. So let's just take a moment to look at a picture here. Here's a picture, my diagram, my graph. What have I graphed? I've graphed my example, which is the square root of x. Now, granted, you could write this as x to the 1/2 power, and you could integrate it like we've been doing all along. But let's suppose we couldn't find an antiderivative for x to the 1/2 power. Then we could draw the graph of the square root of x and divide it into rectangles. And they'll tell you how many rectangles that they want you to use. But today, actually, the picture's already given for you in my 2 examples for today, so you can see how many rectangles. For example, you can see this one's been divided into 1, 2, 3, 4 rectangles. Yeah, just 4 rectangles. And we're going to find the area of each one of those rectangles, and then we're going to add that up. And we're not going to get the exact area because you can see some of these rectangles go a little bit above the curve. Some are leaving out some of the curve, but we'll get a close approximation of the area under the curve, which would be just this. All right, how do we do that? Well, first of all, we have to know the boundaries of this region, which they will give us 0 to 4. So that's why this is 0 to 4. And we have to know the area of a rectangle formula, which is just base times height. Then all we have to do is find the base of each one of these rectangles and the height. Okay, so let's see what we've got. Determine the width of the rectangle. Well, looking at my picture, it's not hard to see that each width is 1 unit long. This one is 1. This goes from 1 to 2, so that's 1. 2 to 3, that's 1. 3 to 4, that's 1. Okay, so each width or base of each rectangle is 1. Now, what did I do? Down here I made a chart. So I have rectangle 1, 2, 3, and 4. So I found that the base or the width of each one of these rectangles is 1. So I put 1 in there for the base. It's not always going to be 1. In fact, they don't always have to be the same. But in this case, they're all 1. Now, we have to determine the height of the rectangle. And there's several ways you can do that, but this is called the midpoint rule because we're going to use the midpoint of the base of our rectangle, and we're going to draw a vertical line at that midpoint and find that height. Because the height could be anything. If you have a rectangle that goes from, let's use rectangle 2, from here to here. The curve, the green curve, I don't know if you can see it under there, but here the height is smaller. As you move along the curve, the height of the rectangle gets bigger. So we have to pick which point we want to use to help us determine the height of the rectangle, and we're going to use the midpoint. So for each one of these rectangles, we have to find the midpoint of the base. So what is halfway between 0 and 1? One way to do it is just add 0 plus 1 and divide by 2. It's 1/2. So my midpoint is 1/2 for rectangle 1. What's halfway between 1 and 2? That would be 1.5, or just add 1 plus 2 is 3 and divide it by 2. You're averaging those endpoints. So 3/2 is the midpoint there. Between 2 and 3, the midpoint is 2.5. I put that here in my chart. And between 3 and 4, the midpoint is 3.5 or 7/2. There's in my chart. Okay, so now I have all the midpoints. But that's not how high, or that's not the height of the rectangle until I take that midpoint, that x value, and plug it into the function. Then that will give me the y value that goes with that x value, and that y value will be the height of that particular rectangle. So I take each one of these midpoints and I plug it into f of 1/2. So I'm going to plug it into the square root of x. And this is why you need your calculator. So the square root of 1/2 came out 0.707. So that was this midpoint. So that's the height of this rectangle right here. So let's just look at doing that rectangle. We know the base is 1. The height is f of 1/2, which turned out to be 0.707. And so the base times the height is just 1 times 0.707, or 707 thousandths. So we multiply that, we get 707 thousandths. And that is the area of the first rectangle. Now let's do the second one. We already know that the base is 1, and the height is going to be f of 3/2. So you're going to plug 3/2 into the square root of x, and do that on your calculator. You get 1 and 225 thousandths. Then you multiply the base times the height. So 1 times 1.225. We get 1 and 225 thousandths. We do the same for rectangle 3. The base is 1. The height is f of 5/2. Plug 5/2 into the square root function. The square root of 5/2 is 1.581, or 1 and 581 thousandths. And then multiply 1 times 1.581. We get 1.581. And again, these won't all be 1s all the time. But we get our area by multiplying the base, whatever it is, times the height. And the last one is the base is 1. And then we do f of 7/2. 7/2 goes in the square root function. And we get the square root of 7/2, which is 1.871. And that's 1 times 1.871. And we get 1.871. Now, we take all of these. These are the areas of each one of these, and we're going to add them up to get the area of that whole region, an approximation for it. So I took all those values, added them up, and got 5 and 384 thousandths as an area approximation for the integral 0 to 4 of the square root of x dx. Now, that's good, I checked it, but let's see if we actually did it by integrating like we've been doing all along. If we actually integrated x to the 1/2 dx from 0 to 4, we'd find the antiderivative. We'd add 1 to the exponent, we'd get 3/2. We divide 1 by 3/2, we get 2/3. We would then evaluate it from 0 to 4. We plug in 4, we plug in 0, we subtract. We do the arithmetic on this, and we come out with 5 and 1/3 for the area, or 5.333. We came out with, for our approximation, 5.384, which is a little bit more, so we have an overestimation of our area, but it's not too far off. So, and in this case, we could find the antiderivative, but the assignment tonight is to do this midpoint rule. Now, if you look in your book, they do a whole formula for midpoint rule, but I think it's easier if you just do the area of each rectangle individually. So I have 2 problems for tonight. One is page 364, number 2. Forget their directions, just use the midpoint rule to find the area under the curve, an approximation for it. And then I have one on page 373. It's in the review assignment. It's number 103, use the midpoint rule. Actually, that one on page 103 is easier, so you might want to do that one first and then go back and do the one on page 364. So try your best. It's a little different. The concept is a little different, but I think you can do it. I think you can handle it. I have faith, and I hope you have a fabulous day. Okay, take care.